Hello everyone and welcome to today's webinar, SIMI EDA Interface A Standards Implementation Best Practices for Equipment Suppliers. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You have joined the presentation listening using your computer speaker system by default. If you'd prefer to join over the phone, just select phone in the audio pane and the dial-in information will be displayed. You will have the opportunity to submit text questions to today's presenters by typing your questions into the question pane of the control panel. You may send them in at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. Today's webinar is being recorded and you'll receive a follow-up email within 24 to 48 hours with a link to view the recording. I'd now like to introduce Alan Weber.
Good morning, or afternoon, or evening, depending on where you hail from. It's a pleasure to have you with us today. This is the third in a series of webinars about the SIMI EDA Interface A standards, and this one is focused on the needs and challenges of the equipment supplier. So we're glad you're with us. Okay, next slide. Pass that one. All right. And the objectives of today's webinar are to give equipment suppliers the information they need to meet customer requirements for the EDA interface implementations on their equipment. This is not stuff that we at Symmetrics just sort of make up. It's actually based on lessons learned from decades of production EDA experience supporting our customers in that implementation. Certainly in an hour you won't become an expert, but I think you'll get a sense of the expert resources that may be available to help you follow on this item. And we'll be identifying additional sources of information at our website and elsewhere. So our agenda today features a quick overview of the EDA Interface A standards by Tammy Tracy. I will then cover some of the highlights of recent purchase specifications, which you receive regularly as part of this overall process. But I'll be showing you what some of the leading chip makers are asking for in their interfaces. Tammy will then take over again and actually show you a sample demonstration of client software and a compliance tester. And then Brian will wrap up with the sort of meat of this session, which is the best practices that equipment suppliers should follow in implementing these interfaces. And so without further ado, let me pass it on to Tammy.
Welcome, everyone. Let's start with an overview. EDA stands for Equipment Data Acquisition, and it is sometimes also called by its original term, Interface A. So how did these standards originate? The EDA standards originated because the industry really needed a better way to collect equipment and process data. Data which is by nature high density and real time. The device manufacturers were evolving their techniques, both fault detection algorithms and run-to-run control algorithms. Data collection needed to be more flexible. A standards-based approach could cover substantially all tool types and would specify a common system that both suppliers and factories could adopt. You're probably familiar with the GEM standard, which can be used to collect tool data, but has certain limitations. Trace data typically happens at 1 Hertz. Event-based collection focuses on substrate movement, jobs, and recipes, and this is good for certain applications, but in practice, it may be difficult to modify the data collection. GEM, as you know, is used for equipment control, and any changes to the host interface may have formalities such as approvals to change, and we want to also avoid even the possibility of causing any tool performance problem. So what the process engineers needed was data on their terms, higher rates of collection, specifically during recipe execution, and for key process parameters at higher frequencies such as 100 Hertz. And this is to feed advanced detection and prediction algorithms. Lastly, it would be nice for it to be easier to define a new data collection plan as needed. EDA is actually comprised of multiple standards that work together as a set. This ladder diagram shows interactions between an EDA client, typically the factory on the left, and on the right, the equipment's EDA server implementation. We start with a request from a client to establish a session to the equipment. A client must be authenticated at the equipment and granted privileges, or being authorized, and SEMI E132 covers this. A client can request a description of the equipment called metadata, or equipment model, and from this the client knows what data is available in the equipment. The client will define plans. To collect specific data under specific conditions. Once a plan has been activated, when the conditions match, the equipment collects the data and sends messages to a consumer web service on the client side. SEMI E134 describes data collection. So let's step into the standards a little bit more. The structure of the equipment is intended to be a hierarchy, which breaks down into logical components. SEMI E120 Common Equipment Model describes the types of nodes and their purpose. Here are the yellow boxes. And SEMI E125 Equipment Self-Description defines the types of data that can be found at each node. For example, state machines, particularly their transition events and related data. Also, simple events, which are non-state machine events. Semi-objects, which are dynamic entities such as carriers, substrates, and jobs. Exceptions, which are based on equipment alarm notifications. And parameters, including status data, configuration, and control values. Now, GEM 300 equipment has additional specific requirements, and these are covered in E164, the Common Metadata Standard. E164 includes specific naming conventions for events and parameters so that there will be consistency across equipment, all suppliers, from the factory's perspective. We want the resulting equipment model to reflect the tool hardware organization, as seen here. It should be logical, easy to navigate. The model should substantially contain the same data collected by GEM, except in EDA, you can understand how the data relates to the equipment, where it comes from, and what are its properties. And as a result, the equipment model metadata itself acts as documentation, which is always available and always accurate. Now, the heart of data collection is the data collection plan. And this diagram is from SEMI E134. A data collection plan, or DCP, can be made up of three kinds of requests. Event requests, which names events and any associated parameters, and covers state machine events and simple events. Trace requests, which are for parameter data to be collected on a given time interval, with optional start and stop triggers based on either events or exceptions. And finally, exception requests, which are based on equipment alarm notifications. Some additional facts about data collection plans: DCPs are defined by the clients and they are persisted on the equipment. Clients can use plans written by other clients, and multiple DCPs can be active at the same time, including from different clients with simultaneous sessions. The EDA standards have established what's called freeze versions. The concept was created to define a set which, upon a certain date, month, and year, ensure that the set of standards are consistent and interoperable. And there have been two such freeze versions to date, Freeze 1 and Freeze 2. The difference is primarily in the web service message formats and message protocol version. Freeze 2 is the current version. Now, the freeze versions and the E164 standard are independent of one another, and their requirements are orthogonal. What we find currently is that most device makers who require Freeze 2 also require E164, and there is a future Freeze 3 under development, and we expect that when it's ready, all device makers will require E164 also. Next slide. So my final slide compares GEM and EDA. Note that EDA is in use today in leading global 300mm wafer fabs. And here is Alan Weber next to tell you more about what to expect in the equipment purchase specifications.
Thank you, Tammy. That was a great quick overview. And now we're going to cover highlights of recent purchase specifications. We'll start actually this section with a quick survey to see how many of you on the equipment side in particular have received a new EDA purchase spec in the last 24 months. The EDA sections of the EDA purchase specs actually are typically part of an overall equipment automation requirement spec. There'll usually be a section focused on implementation of standards, and part of that will include the EDA interface standards. These sections can vary from just a few pages that reference the actual standards all the way up to maybe a 20 or 30 page section. So they vary all over the map. Okay, we can see here, let me move this control panel away so I can see the results. Okay, there's a lot of don't knows here. There's some that have, yeah, got it. Okay, well, so this topic will be, I think, germane to a lot of the don't knows, because if you haven't seen one of these lately, this would be useful information for you. Since we help our equipment supplier customers implement these standards, we typically get to see the specific fab purchase specs, from those customers. That is all, of course, done under NDA, and that information doesn't move anywhere beyond that relationship. But from surveying that kind of information, we can tell you that some of the lightest specs are just 3 pages with a potentially incomplete list of the standards and no additional guidance. This is not going to give you really much information on which to base your implementation. There's some specs that include a lot more, let's say, bulk, but not necessarily more useful information. They may copy information out of the CIMI standards or earlier presentations, but still don't provide the kind of guidance that you need to truly meet the advanced user requirements. There are other cases where information may be scattered across a combination of Word documents, spreadsheets, handwritten notes, napkins, presentations, who knows what all. But it's hard to actually assemble that into a cohesive spec from which you can do your development. Our target in helping some of the factories actually create a good, robust spec has been something in the order of 15 to 20 pages that does not actually repeat the information that's in the CIMI standards, but provides complementary information that describe what their expectations are from a model content, what performance they expect in terms of number of DCPs and data collection rates, what expectations they'll have regarding testing and acceptance requirements and response formats. So I think over time you will see more and more consistent incarnations of these specifications as people understand what the best practices are. So, okay. I mentioned the model in particular because this is one of the areas that is most important in an EDA interface. As you'll see from this diagram, requirements are developed from the factory side sort of backwards. The factories need to implement some set of KPIs, management metrics based on the kind of factory that it is. And here's a sampling of some of those KPIs. But at the end of the day, what achieves those KPIs are applications that largely depend on equipment data. In an EDA interface, the only data that you can collect is information that is in that metadata model that Tammy just described. And so that essentially forms the contract, if you will, between the tool supplier and the factory. And so it's very important to specify clearly what the factories expect in that model to ensure that the data will be collected that can support those applications. The actual model and the interface is built from the left side. The equipment components are analyzed and put into a specific model by the equipment developers, which if they use symmetric software can be a fairly straightforward process of creating the EDA model on which the data collection is based. But again, this process is very important, and it starts with a good requirements spec. Okay, an example of the kind of things that you might see in a specification describing an equipment model beyond what's specified, by the standard itself, are some of these examples. For example, key process parameters. The standards don't talk about anything that is process specific. They refer to things like substrate movement, job control, carrier management, and these kind of things. But anything that is specific to a process is really left to the factories themselves. So you may see sections that include explicit process parameters to support different applications. Control parameters for operating mechanisms is another example. If you've got a number of PID control loops in the equipment managing the fundamental pressure, fluid, temperature control, looking at those parameters is not something you typically see, but you may want to. Also, built-in data collection plans for monitoring common failure modes. Nobody knows the equipment better than the people that create it, and so I think over time you'll see more and more end users saying, hey, please provide with your equipment some built-in data collection plans that allow us to enable them and monitor the things that might be issues. So these are, again, these are expectations that are growing over time. And you can see the rest of the list there: platform and tool performance parameters, countdown timers for lot completion, nodes for field down to the field replaceable unit level, and anything else that's necessary to support the stakeholder use cases. So one of the services that we offer factories is to help them actually structure this kind of information into a purchase spec. So this slide kind of shows what a common structure for that would be. Again, there'd be a section on references to which standards are required, which freeze versions, which parameters, but not really repeating anything that's out of the the standards themselves. Also, something on platform and system architecture. Brian will have a lot more to say about this in the last section, but we've seen all sorts of examples about good system architectures on which the EDA interface is built and bad architectures. Of course, there would be a meaty section on the standard specific items, so augmentations of the individual standards that you see listed there, more details on model content, and then performance, data quality, and acceptance testing. And I'll say a little bit more about that in the next two slides. Finally, of course, the specifying an interface like this is not something that happens overnight, and the lifecycle interactions between the factory and the tool suppliers is another area to cover. For example, long before the equipment is developed, it could be useful for the factory to see what the model content is going to be, so they can analyze it for its suitability for their application content. And this could be provided as an export from the equipment, months before the tool itself is delivered. And there are other things that fall into that category. And of course, having structured the requirements in a well-defined way, having a response checklist that makes it easy for the suppliers to highlight the areas where they have fully complied and areas where they may need some further work is a good deliverable to have here. And it also makes the evaluation job on the factory side a little more straightforward. Okay, I've got a couple of excerpts from sections that you don't always see in these specifications, and that's in the Number one, in the performance and data quality area. Since EDA is not just you saw the data collection plan that Tammy showed. Well, you can have a few of those or many of those in a given equipment. You can have them be very simple or very complex or anything in between. And so just specifying a total bandwidth as a metric is not really sufficient to convey the actual potential use of that equipment and that interface. And so the performance and data quality section should reflect what the data collection techniques are going to be. In particular, they should address how many parameters per tool and what the sampling interval, the maximum sampling interval is likely to be. A group size of 1, this basically says every time you have a sample, please send it. There's a way of grouping and buffering data in the data collection plan definition. Again, as Tammy mentioned, this is a multi-client standard, and so the spec should indicate the number of simultaneously active client sessions that you might expect, all with that capability above. Large equipment may need to handle an even faster data collection rate because of the needs for evaluating and analyzing data from that equipment. In these cases, maybe the rates that are quoted would support a group sizes greater than 1 and also buffering to achieve the performance. So, and then finally, all of these parameters should exhibit some data quality characteristics like, following the Nyquist sampling rate to make sure that you're actually getting data at the rate you can observe the phenomenon, making sure that your trace reports are consistent, that they're not drifting away from the baseline. So there's a lot to specify here that you don't typically see. On the other side of that coin, of course, is how are you going to, at the factory side, test those requirements? And so ISMI years ago wrote a very complete testing methodology down that can be followed with commercial software. And Tammy is actually going to demonstrate one instance of that here in a few minutes. But those performance criteria that were specified in the earlier section should be tested to make sure that they meet the requirements under the whole spectrum of expectations. There's actually another piece of software developed years ago by NIST under contract with ISMI that checks the model content to see if it matches the E164 structural and naming convention requirements. And you can kind of think of the designing a test as sort of a design of experiments. You're varying these different parameters across the valid ranges in terms of number of DCPs, size, number of parameters, sampling intervals, etc. So making sure that the testing follows the actual requirement. Okay, final slide I've got here is just to show kind of where the adoption has been. This is, although we call this a new standard, it's been around for really almost 15 years now. Adoption started slowly with Global Foundries, AMD actually at the time, and Toshiba, but in the last 5-6 years has really picked up as the foundries and IDMs across the world have realized its value for supporting advanced applications. And so we're on a pretty steep adoption curve at the moment, and so that tells us that there's a lot of interest by the customers, and so you equipment suppliers are probably going to see a whole new wave of requirements that follow some of the guidelines that I've just shown. So, all right, with that, let's turn it back over to Tammy to show you a little bit of how some of this software looks.
Thanks, Alan. Yeah, so we're going to demonstrate 2 EDA software applications. And the first is ECCE Plus. ECCE stands for Equipment Client Connection Emulator, and ECCE Plus can be used by equipment suppliers to confirm the metadata model of your equipment and to develop data collection plans, and this will help demonstrate that the equipment is producing the data that you expect it to. And the second piece will be EDA Tester. EDA Tester is a test application designed for compliance to the semi-EDA standards and for evaluating performance of data collection. And both of these applications are useful for suppliers as well as factories. Now, this demonstration has been pre-recorded.
In this demonstration, I will be using an equipment simulation which includes an EDA server implementation. I'll start ECCE+. When it is launched, it presents a list of session definitions. A definition includes the network addresses of the EDA server web services, the client name, and the equipment name. Interface discovery can be used to query the equipment for network addresses. Connect sends the equipment an established session request and starts a consumer web service to receive equipment data. The session is established. Requests were automatically sent to the equipment to collect the equipment metadata, shown in a hierarchy here. Navigate the hierarchy nodes to browse the model and click on a node to view its properties. This model is compliant to the E164 standard. It is well organized. The model includes the physical components present in the equipment, for example, an EFEM. It includes logical elements like the job manager and the material manager, and it represents the processing chambers. The chambers include process parameter data, a representation of the processing location in the chamber, and because the process chamber executes a recipe, the model includes a module process state machine from E157. ECCE lets us send a request for immediate parameter values. I can do here. And also to create data collection plans. Here we see several existing plans. A data collection plan can contain more than one type of request. Here I have one which includes an event request, an exception request, and a trace request, which includes start and stop trigger conditions. ECCE Plus includes the ability to create and edit plans by selecting elements from the hierarchy. A data collection plan is defined on the equipment, and the equipment persists them. Activate a plan to initiate data collection. Multiple plans can be active at the same time. Data reports can be viewed in several ways. The SOAP log contains new data messages. The Data Reports tab shows the message content in raw format. We can see the data in tabular format on the Live Data tab, or numeric data plotted on the strip chart. You can also collect data to a CSV file for offline analysis. For example, these files. And I have one more feature to show you. In EDA, multiple clients can have sessions simultaneously. If a client has security admin privilege, then it can manage the access control list and existing sessions on the equipment. Let's look now at EDA Tester. On the left side, we see a list of existing equipment definitions. The details for an equipment are the same as we saw in ECCE+. We have the network addresses for the web services, the equipment name, and the client name. We can use interface discovery to query for an equipment. We're going to perform a quick connection test, which briefly establishes a session to the equipment, and this will help us ensure that the tests will be able to run. Using Save Equipment Metadata, we can write this equipment's metadata out to files that can be later used with the program from ISMI called the Metadata Conformance Analyzer. MCA checks the equipment model for compliance to the SEMI E164 standard. You'll need these files for that tool. Configuration is also required for compliance tests. Specific information from the equipment metadata is used to define which exceptions, events, and parameter data will be used in the data collection requests. Equipment also needs to provide one built-in data collection plan and one client ACL assigned the E132 security admin privilege. Compliance tests correspond to the ISMI EDA evaluation method document, Appendix A, Procedures A through G. This includes establishing sessions, querying for metadata, metadata notifications, DCP definition, activation, and deactivation, built-in DCPs, persistence of plans and sessions, and multiple client sessions. Each test contains steps. Each step includes a description, expected result, and a space for actual results. Select one or more tests for execution. Some tests require user input. You can watch the progress as the tests execute. This test is prompting for user input. The test results can be seen by selecting each step and the overall pass, fail, or cancel status can be easily seen. A test report is generated. It includes the configuration and a summary of each test. Let's look at performance testing. Performance testing evaluates the equipment data collection performance under varying demand conditions for parameter trace data. The test configuration is like a multi-dimensional matrix. A test is made up of many iterations. Each iteration selects a trace interval, a number of parameters from a process chamber, a group size to control the number of reports per SOAP message, and the number of process chambers in the equipment. The total execution time of an iteration is assigned, and the maximum allowable latency is assigned. Latency is the time difference between perfect timing and the actual timing of data reports. Exceeding the maximum latency will cause a test iteration to fail. During test execution, we can observe the current status, including the instantaneous number of parameters per second being collected and the maximum latency observed in this iteration. On the Latency tab, we can see a chart of the latency values based on the timestamps in the new data messages, including the collection time, the time the data was put into a trace report, the time the trace report was put into a data collection report, and the time the client received the new data SOAP message. This test will run for several iterations, and I will stop the test at this point. At the conclusion of the test, we will see the results, which includes the current configuration, the data collection plan used, and statistics on the latency. This information is also written to file. There are some options for tests to run. You can run a predefined test. You can run a custom test where you specify the iteration parameters, or you can define a plan where you select from existing DCP definitions to be used during the test. This concludes this product demonstration.
Okay, so we're going to go into a quick poll question. And this is, does your company use automated test software to check the compliance and performance of your communication interfaces? And this can include not just EDA, but GEM. So let's flip over and start looking at our results. Oh, very good. So a lot of you are using automated test products. That's wonderful. And if those of you who are not or would like some more information, please reach out to Symmetrics, because we also have automated test products for GEM and GEM 300 equipment. And next we're going to hear from Brian about best practices.
Thank you. Let's start by thinking about the perspective of the end user, the EDA experts at the factory who are receiving the equipment and validating it and setting up EDA to be used. And some of their primary concerns are ensuring that they're going to get the performance from the EDA interfaces and the data quality and the reliability with extended use. And they are, of course, highly concerned because they have to maintain the product throughput while maximizing the EDA data collection. And they know that they're going to have to deal with some equipment defects, and they have to figure out how to build in the right level of tolerance for these defects that they know they're going to see some. One of the first things they have to figure out is requirements for each tool type. This is particularly difficult because essentially they have to use a crystal ball, because they don't really know up front what kinds of data they're going to need, because the future is simply unknown. So we'll talk about that a little bit and how to address that and help them. They also, of course, have to be building these operational support tools for managing the data collection plans across the factory, synchronizing timestamps so they can analyze the data, and many other logistics involved. To try and help them, let's look at our top 10 EDA implementation best practices to try to help them be successful. And first and foremost, we need to understand their real requirements. And one of the keys to doing this is to make their job as easy as possible. They are going to provide and create purchase specifications they're going to expect standards compliance. I mean, not complying to the standard just would be a terrible flaw. So that's going to really be expected there. And the key to understanding their real requirements is recognizing the key applications that they will be running where they're using EDA. And we know they're going to be creating and running predictive maintenance applications, fault detection, statistical process control, and many big data applications that are feeding, for example, artificial intelligence algorithms. And these algorithms are used to collect lots and lots of data, and they just don't know ahead of time all of the data they're going to need. So you need to understand that, and as an equipment developer who are the real experts on the tool, you simply want to understand and focus on what they're going to be doing, and I'll come back to that a little bit more. And you also want to consider the non-functional requirements. Essentially, you get to decide as an equipment supplier what your maximum sampling rates are going to be, how many parameters per data collection plan you're going to be able to have. And we know that they're going to need to be running EDA 24/7. So you really need to consider how it's going to be used, which the data collection is going to vary from 1 week to the next, possibly from day to day, but more likely week to week or month to month as they're collecting lots and lots of data. And simply recognize that it needs to be a high availability interface. The data collection and algorithms just won't work unless they're collecting lots of data over a long period of time. And make it easy to use and configure. And of course, you want to define a robust system architecture. And one of the ways to do that is to separate the EDA server that's publishing the data from the real-time equipment controller. And this is to ensure performance that and you also, one of the things you want to look at is your internal data pipe and how the software has been designed to push data from the source of the data until it gets all the way into the EDA messages. Of course, if you have a slow internal data pipe, your EDA interface will be equally slow. And your smallest bottleneck will ultimately determine the performance of your system. It helps if you minimize the number of software layers from the source to the message. Process data is usually considered the highest priority, so design that into your system. And sometimes it helps to, in fact, it almost always helps to really decouple your internal data transfer from the external data reporting. And this is because of the nature of EDA, where you're going to have people collecting data at different rates. You could have several clients collecting the same data, but at different rates. And you can increase your efficiency by decoupling your software to manage that better. And in some extreme cases, you may have to re-architect your system. If you've designed your system 20 years ago, it's not going to meet today's data collection demands. Also, be sure to choose a platform with lots of extra headroom. Hardware is pretty inexpensive, quite inexpensive compared to downtime and the cost of support if you've chosen badly. In particular, pay special attention to the speed of the CPU you've selected, the number of cores, and especially the amount of RAM. Those are the two most important of your hardware specification. Of course, you need enough disk size as well, but make sure you have room to grow. The Today's operating systems really, like all forever, they don't like to run at a maximum CPU usage. They perform significantly better when you're keeping them, even in a high data collection situation. You really don't want your CPU running over 50%. And you need to plan for that and expect that you might even be doing upgrades later in the future. So you need to leave that extra headroom when you're choosing your hardware. Tammy talked and showed a bit of the E164 standard and how it helps you to create a very well organized equipment model. Equipment modeling is typically the largest effort of implementing EDA on an equipment. It just takes time and care to design it in a way that makes sense to the end user. We want the end users to be able to find the data they're looking for easily and quickly, and it should be logical to them. E164 helps to make that possible by telling you how to organize your data. And it's not really any more difficult to do E164 than it is to not do it. So it's really better to do it. And in particular, this is helping you if you are implementing GEM and GEM 300 on the equipment, then it is almost critical that you are complying with E164, since it basically tells you exactly how to model these GEM 300 standards in your interface. And it is so much easier to use an EDA interface when you can anticipate where all of the GEM 300 features are going to be. Of course, you want to use modern software engineering practices. Software engineering is a very fluid industry still. The practices from 20 years ago, 30 years ago, are almost completely different today. And you need to be using the modern software practices. Make sure you're designing the EDA software to run 24/7. Design it to be used heavily, where they're going to maximize the you need to maximize its performance because it's going to be used to its maximum. And of course, you need to include unit testing, system testing, and regression testing to ensure. I mean, if you're not testing it, it's not going to be as reliable as you think. And as I mentioned early, the factory doesn't really know at the beginning what they all need. The equipment manufacturer is the real expert on the equipment and the processes and the hardware. So it's really your job ahead of time to anticipate what data they're going to need, what data they're going to need today, tomorrow, and in 5 years, and maybe in 10 years. You need to be thinking ahead and giving them the data that they're going to need in the future to solve the problems that are going to be showing up in the future. One thing you can do to really help with that is in your E157 implementation. The E157 is describing the execution in your process module, or if you're a test equipment in the steps that the test equipment is doing. And E157 allows you to break down the execution of your recipe into explicit steps. These steps, every time a step is starting and finishing, there's going to be collection events. And these, particularly in EDA, are extremely useful because it allows the end user to set up the trace data collection with very high speed data collection during particular phases of the recipe execution. So taking the time to design E157 allows your customer to set up more efficient data collection. And the basic principle when you're deciding which data to publish, when in doubt, you should include it. And they will very much appreciate that. And that will save them from having to ask for updates later and patches later that might provide more data. It's much easier just to provide more data up front than it is to add them later after an equipment has already been shipped and installed at the factory. You also want to design in hooks for field service support. If there is a problem, you want to make it easy to diagnose the problem. In particular, one thing that Alan mentioned was the built-in data collection plans. If you can design built-in data collection plans that are able to express the health of your EDA software, that is extremely valuable for you and for your customer to help diagnose any problems you might run into. That can be done ahead of time and very deliberately, and is well worth the time to have meaningful built-in data collection plans. And of course, make it easy to install and turn on the EDA software as well. Now, coming soon in the future related to these EDA Interface A standards are the Freeze 3 version of EDA. Today we have 2 versions, and there's going to be a 3rd version. And here's the major changes. That includes a change to from SOAP XML to gRPC technology, which is a binary interface. This is to increase performance possibilities. It will allow for less bandwidth to be used for the same data. So it should allow us to increase performance expectations across the board. Also look for passwords to be added to the client sessions, as well as a new feature called cached data, which is reserved for super high frequency data collection for particular pieces of data and particular processes. This won't be used across the board for all data, but when you have super high data collection frequency needs, this new feature is going to fill that gap. And look for the equipment modeling to be simplified. Finally, we do recommend using proven commercial software. Developing software that's robust and well designed is a lot of work, and companies like Symmetrics, this is one thing we do. This is all of our focus, and by us focusing on this, it really allows your engineering team to focus on your tool differentiation and other intellectual property that adds value to your equipment. So we recommend choosing products that are proven and mature in the industry. And at Symmetrics, we do provide a series of products. For the equipment side, we have SimPortal Plus for developing EDA. On the client side, we have ECCE Plus, which Tammy demonstrated a while ago to manually interact with an EDA interface. We also have EDA Connect, a .NET library for developing clients, EDA Tester, which Tammy demonstrated. We also have Sapience, which is a platform designed for developing data collection applications, where it's actually designed with the cloud in mind, as well as on-premise installations and hybrid type systems. And thank you very much. We would now like to open up for any questions that people might have related to anything we've talked about.
Thank you, Brian, Tammy, and Alan, for your wonderful presentation. So we're now going to begin answering the questions submitted during today's presentation. Our first question is, how can the EDA tester software test the performance on an interface when the various fabs may have different requirements?
Tammy, you want to take that? Or you
Well,
want me to?
sure. I mean, I'll answer it quickly, and then maybe you can add, Alan. It's for certain the factories will have individual needs for their performance testing and their own thoughts about what makes good performance for them. For you as a supplier, I would suggest that you use EDA tester to not just envision what is a nominal data collection for your equipment, but try to really push the envelope and ensure that you can collect data at even higher rates of collection. Alan?
Yeah, let me add to that. Thank you, Tammy. You'll notice in Tammy's video there on the performance part, there was a table of parameters that you could configure with a user-defined test. So the number of parameters per DCP, the max number of DCPs, the group size, latency, all of those things you can are designed in there to be able to match whatever range of those values shows up in a requirement spec. So hopefully you can test pretty precisely to the specific requirements you get, and in that way match very different fab requirements. Good question.
Great, thank you. So this one's a two-part question. What is the status of the new Freeze 3 version of the EDA standards, and how soon do we need to begin considering its implications?
Brian?
Yeah, I should probably take that. I'm highly involved in the committee working on this and the ballots. And where we're at right now is there's a bunch of ballots open. We've gone through about 6 iterations of voting on these ballots related to Interface A, the E132, 134, 125, and it feels like we are very close to consensus. We'll find out here in a couple of weeks, but the mood of the task force is that we're getting pretty close to consensus, and that should be achievable this year. What remains is the some of the I think it's E125. A ballot for the gRPC implementation has not been submitted yet, so that's kind of the final straw. And the E164 ballot also has not been submitted. Those are the only 2 things left. I don't believe the E125 gRPC will be controversial at all, which really leaves E164. When that's once that ballot is done and submitted, that'll be the last thing we need. So I would look for by the end of this year, next year, we should be having that. The other plan for the industry is to allow prototyping soon. The expectation is after this round of voting, we think we'll have enough consensus to post files, the technology files, to the industry so people can start experimenting with it, testing with it. And the task force wants to arrange a meeting where different suppliers of the software get together in the same room and just try it out together and see if we have any issues left to work through. But that should happen this year in a few months.
Would that be sort of interoperability testing, Brian?
Yeah, make sure that one software's client and one, another's server, that everybody can talk to everybody, client and server, server and client. So yeah, do an interoperability test between different suppliers of the software and anybody who wants to participate. So that should be happening this year for sure.
Great,
Okay.
thank you. And I know we're getting close to the top of the hour, but we have such great questions. We're going to try to squeeze a couple more in. So will E164 be considered an essential component of Freeze 3?
Yes.
Yeah, the answer is a resounding yes. Yeah, and I think the strategy for E164 and Freeze 3 is going to be to simplify it. I think it's been an overwhelming requirement for a lot of folks because it mixes some really big principles with a lot of minor details. And so I think the approach to E164 will be to greatly simplify it and focus on the things that really make a difference in the interpretability and usefulness of the metadata models.
Yeah. And on the task force, those who opposed keep adding E164 into Freeze 2, at the same time they were opposing it, were expecting it to be part of Freeze 3.
Great. And this is our last question for today. Will gRPC be mandatory when Freeze 3 is defined?
Yes.
Simple. Okay. Well, thank you all so much for your presentations today, and thank you to the audience for joining us. On behalf of Symmetrics Connectivity Group and our presenters, thank you for joining us today and have a great rest of your day.
Thank you.
Bye all.